Hi, math lovers. Welcome to notes number 140 on linear programming. I want to make sure that you read the section in your textbook on linear programming. We're going to use a graphical approach here, and you can see as they go through, they have a nice feasible solution. Every point in the shaded region is going to satisfy the constraints. And what you want to remember is the optimization, the optimal solution will occur at one of the vertices, so at the corners. So it's important that your graphs are really on task for these. There is a very nice set of directions on page 710 for you to use, and that's what we're going to be basing our graphical approach on here. Okay, so I have an example for us. It's number 33. What we're going to do is we're going to first take our constraints, we're going to sketch them, we're going to find our vertices of the constraints, and then we're going to test them in the optimal solution. All right, so just like it says in the book. So our optimization, what do they call it? The maximum value, find the maximum value. Let me see what they want. Number, oh gosh, 116. Our objective function, the objective function. So they want us to find the minimum and the maximum for both of those for our objective function. Okay, so they're going to give us our constraints. X is greater than or equal to 0. Y is greater than or equal to 0. So I know I'm only working in quadrant 1, okay, which is very nice. Okay, X plus Y is less than or equal to 1. I'm going to think about this in slope-intercept form. So y is less than or equal to negative x plus 1. So that means I'm going to go up 1 here, right? And down 1 over 1. And I'm going to draw a line. I don't have a ruler with me, so a solid line. Okay, pretend that that's straight. Pretend that it's a straight line. And I want it to be less than, so I'm going to shade below, okay? I'm going to have greater than, so I'm going to shade above that section. And then I have, so maybe if I think about it like this, I'm going to shade below, okay? And then I have 2x plus y is less than 4. Let's rewrite that as y is less than or equal to negative 2x plus 4. Okay, so 1, 2, 3, 4, that's up here. So down 2 over 1, down 2 over 1. Okay, so that's this line here. All right, and then they want less than, so that should be below this point too. Okay, so I'm going to look for a section that's all of these parts, and that's going to be this region right here. So a couple things. This constraint here, this is extraneous. Okay, there's no reason for us to have this. It doesn't do anything. All right, so we're looking at this little section right here, and my coordinates, my vertices that I'm going to need to test are going to have to be 0, 0. I'm going to have to test 1, 0, and I'm going to have to test 0, 1. Okay, and I'm going to put each of these, so these are my 3 vertices right there, and I'm going to put them back into the original objective function that they've got up there. So I'm going to squeeze this in over here. Z is equal to 3x plus 4y. Let's go ahead and see what our values are. So the Z is equal to 3 times 0 is 0, 4 times 0 is 0, so that's 0. Okay, really exciting. Z is equal to 3 times 1 plus 4 times 0, so that's just going to be 3. And Z is equal to 3 times 0 plus 4 times 1, which is going to be 4. So they want to know what our maximum value and our minimum value are. All right, so my maximum value is this value of 4. So the maximum is going to be at the ordered pair 0, 1. And my minimum value is right here at 0, and that's going to be at 0, 0. Okay? And there'll be lots and lots of applications that we're going to use for this in the next day, word problems. But today, I just want you to focus on exactly what the directions say. Start with your sketch of the constraints, okay? Find the vertices, and then you're going to test the vertices in the objective function, right? Really try to be neat. It's going to be important. Have fun with your problem set.